First responder teams need to plan and act fast. Their plans are often negotiated on the fly. For a team of humans and robots, a human operator must translate the agreed plan into machine instructions for the robots. The robots also need to coordinate the execution of their tasks with the human team. These human-robot interactions are a significant bottleneck in deploying autonomous systems in rescue missions. We aim to reduce this translation burden of programming and deploying autonomous systems by inferring the final plan directly from the human team's planning conversation. The input to our algorithm is the human team's conversation in text form. Disaster response teams are increasingly planning missions using web-based tools. We designed a web-based collaboration tool that is modeled after the Nix system that is currently being used by first response teams. The web tool contains situation information, a chatting window, and a map.
I think we should plan to have as many people working at once as possible.
Divide the whole space and send red robot to check room A to D, blue robot to check H to E.
Wait, but then we have one time step where A and H are being checked, and there is nothing for the other teams to do. Partition is good though. So how about...
Okay, you're right, but I just noticed we have people in problems in rooms B and G. So step 1, B, blue...
doing step 2 like that isn't good for the other crews, since there is only one mechanic and 2 meds.
Correction with robots. Step 2 would be F red and C blue, and step 3 would be... Hey, red robot got damaged.
Okay, we only have one robot now.
Send blue robot to B, then G, then D for human rescue.
B, G,
Other
D...
option is B, C, G, D.
I think the humans should take priority. I like the first plan better.
We transformed the raw conversation into a more structured form. This structured form contains the actions discussed and the relative ordering among those proposed actions for each utterance. This form of data captures many characteristics of human conversation that make plan inference challenging. Our approach combines probabilistic generative modeling with logical plan validation used to compute a highly structured prior over possible plans. This hybrid approach enables us to overcome the challenge of performing inference over the large solution space with only a small amount of noisy data from the team planning session. The output of the algorithm is a distribution over plans. The most likely plan is delivered to the robot for execution.
Okay.
Room G is ready for room medical team.
Okay.
Room G is ready for red medical team. Room A is expected.